Okay, so good morning everyone and welcome back for the second session of the Manufacturing Systems Engineering course for yourselves. I hope everyone's had a good week and you didn't have a particular task to do over the week that's just gone, but I know Adelaide asked you to meet in your groups and speak about the product that you were going to look at as part of your group work. I'll be here in the background as ever today, so if you have any admin questions or any course related questions, just drop me a message on the chat either to the group or in private. But otherwise, I will pass over to Michelle, who is our head of engineering division. So she'll be able to make an introduction of herself and she'll be leading this morning session.
Okay, good morning everyone. Just to ensure a smooth transmission, my bandwidth's pretty poor, so what I'll do is I'll switch my video off. I just wanted to let you all see me this morning and say good morning. So I'll stop my video and I'll start sharing my PowerPoint. If you could please let me know if you can see my screen.
Yeah, that's great.
Yeah, I can see that.
That's perfect. Okay. So today, for the second module, Manufacturing Systems, I'm covering quality manufacturing with you. And this course has been designed by myself and Adelaide, who I know you know very well. So, I don't think I've met you before. I did sit in some of your presentations from the previous module. But for those of you that don't know me, I'll just go ahead, just some facts for me. As Janet said, I'm head of engineering. I'm actually a mechanical and manufacturing engineer. That's my background, but I have specialised in quality and project management. So I've been teaching, I've been doing consultancy and research in quality for the last 25, getting on for 30 years. I started my career in shipbuilding, so for those of you from the naval side, from the shipbuilding side, then I've got some facts and things I can share with you from my experience of shipbuilding, although it was quite some time ago, so it'll be interesting to see how things have developed in that time. I'm a certified Lean Six Sigma Black Belt and a Senior Fellow of the Higher Education Academy. And my publications in terms of research is in quality and lean manufacturing, those two fields. So I'm a reviewer for the Total Quality Management Journal, the International Journal of Six Sigma and Competitive Advantage, and the Journal of Cleaner Production. And I also sit on the Chartered Quality Institute Research Advisory Panel. So that's a little bit about my background and what I'm bringing to the course. I'll bring my experience, but I'd quite like today to be interactive. So although I've got a lot of information to pass over, so feel free to come in with questions and we'll do some breakout rooms as well. So at the end of this session, you should be able to define what product quality is. We're going to look at quality characteristics and classifying them. Now, I know you've had a sight of your work, your task for this particular module, and part of that is to sort of identify your quality indicators. So we'll have a look at that today. We'll look at sort of inspection principles and then we'll have a discussion around that in terms of BAE systems and your roles within that. We'll look at some of the modern inspection technologies and we'll look at process capabilities and tolerances moving on from inspection. So we're going from inspection to try and do prediction and prevention. And part of that's statistical process control and look at some of the other programs in manufacturing, so TQM, and next week when we look at lean manufacturing. So it's always good to know where we've come from. So a little bit of the history and trying to look at how the sort of industrial revolutions have shaped, you know, the development of quality throughout the last couple of centuries. So if you take sort of pre-industrial revolution, if you like, the first industrial revolution was the mechanisation and the steam power. Before that, you had a sort of craftsman, and in terms of quality, way back in the 1300s, they started to look at the European guilds, and we had hallmarks coming in as standards of quality, and that was the sort of pre-industrial revolution. And then as factories started to emerge with the steam power in the sort of mid-1700s, you started to look at more product orientation and how quality could be built in a sort of more factory situation. And we had the likes of Frederick Taylor, who brought about scientific management. Very much the focus was on inspection and quality control going into the 1800s. Within that, we hit the second industrial revolution, which was more mass production, and that was brought about by electricity, oil and gas. And we had, as I mentioned, you've got Taylor and Ford really coming into bringing out this kind of quality control and inspection. But moving on to the sort of early 1900s, we started to look more at process orientation, and that started to coincide with the third industrial revolution, which we started to see automation, information communications technologies. And in the sort of process orientations, where we had the sort of early 1900s, we had statisticians such as Stewart looking at how quality could be improved at the process level. You might not be familiar with some of the sort of quality gurus, but during the war, or sort of post-war Japan, they really pioneered a lot of the techniques, and they brought across the likes of Deming and Duran to Japan to improve their quality and really give them a competitive edge. And they were very successful in that. The war, Second World War, really triggered the military standards, and we today are looking at ISO 9001 2015. Has been the later developments from that. Within shipbuilding, I'm sure you'll work to ISO 9001, but you'll also have your own quality standards that you need to work to, and that will be the same for any of you that work on the air side as well. Total quality management then came along in the sort of late 1900s, and that encapsulated the whole organisation and everyone being involved in quality. But we're now at the cusp of something called Industry 4.0, and people are predicting this is going to be the fourth industrial revolution. And we're moving more to artificial intelligence, virtual reality, moving into the Internet of Things, big data, machine learning. And there's so much capability out of that for quality, that the sort of whole way that we're managing quality is on this edge of change. And we can bring some discussion into, when I'm going through the concepts, what I'd like is to bring in some ideas of, okay, so what does that mean for us? This is how it is now, where are we going in the future? So what does quality 4.0 look like? And many researchers at the moment, that's what they're focusing on. But going through the sort of timeline, we start off with inspection, and we can still see inspection today. And I will be asking you, what kind of inspection methods do you use? We looked at, the quality control starts to come in. We're going to bring in statistical process control. How do we move from inspection to prevention? And also we've got, how do we assure quality? So we've got standards such as ISO 9001 for the quality assurance side. And then we start to look at continuous improvement and innovation through total quality management. And as I said, we're now moving on to quality 4.0. And we still don't really know what this quality 4.0 is going to look like, but authors are starting to write about it, starting to look at how we can change, how quality is changing, and hopefully for the better. So to give you some information on this Industry 4.0, because you may or may not be familiar with it, and you may start to see in your company, in your area, some of the new technologies, that are happening that are going to enable this. So what I'm going to do, I'm going to see when I'm sharing, if I share my, I don't know if this is going to work. Okay, can you tell me if you can hear this video? If I start to share this link, can you tell me if you can hear it? If not, I'll have to find a way of sharing it otherwise. I'm just going to stop sharing this for now. Right, let me see if I can share again. Can you see this video, the KPMG video? Could someone let me know if you could see this, please?
Yeah.
Perfect. Let me know if you can hear it too. Can you hear it all right?
No, I've no sound.
No.
Oh, no sound.
Let me see. Let me try stopping sharing it and let me see if I can share again.
Otherwise, we can always put I can always embed it into the online course, and then they can go and have a look when they go into breakout rooms potentially, Michelle.
Okay, we could try that. Let me try one more time. Share web browser. Let me just do one more thing. If it does multimedia. Is this going to work? Can you try this? Let me know. Can you hear it? No?
No, nothing yet.
Okay, I think, Janet, if you could share it, then
That's fine. I'll grab it just now. Is the link on the slide? Yeah, I can grab it and put it onto the course.
the link, yeah, the link is on the slides. I'm sorry about that. I wonder why we can't actually get the sound. Let me just see. Okay, hang on. I think I might be able to do it now. I'll try one more try. This time?
Yeah.
That's it.
The fourth industrial revolution has begun, and you have the chance to be part of it. this isn't going to be like before. It's not about the steam that powered our factories in the first revolution, or the mass production model that dominated the second, or even the emergence of computer-driven systems from the third revolution that we're living in today. Industry 4.0 is about connectivity. It's an opportunity to radically change the way industry responds to the needs of society. As previous industrial revolutions were led by innovations in manufacturing processes and systems, the advancement of Industry 4.0 will be driven by a smart, interconnected, pervasive environment. The opportunities for disruption are huge, and those left behind will feel it acutely. Still space for leaders of this new revolution to emerge, but the race has already started. Understanding what current leaders are doing will help you join them. KPMG formally examined what those trailblazers were doing in their factories and their offices, and it revealed some thought-provoking findings. Our research highlighted a number of areas that current Industry 4.0 leaders are focusing on. Leaders are planning ahead with clear strategic vision, driven by performance and tying investment to proven opportunities for growth, progress, and innovation. They are focused on discovering how smart products and processes can be developed. Integration is key. Silo-driven development, which limits scope and value of new projects. Instead, they are moving towards large-scale and proactive integration across their enterprise and among their customers, supply base, and products to ensure they are aware of every possible opportunity Industry 4.0 technology has to offer. Perhaps most important, bold. This means nurturing innovation, developing disruptive thought processes aimed at devastating the status quo, and looking for opportunity in every element of their value chain, from which products are designed and how they are produced, to who they are sold to and how they are purchased. Your organization may be radically different in the future, with a range of products, services, and processes you can't currently predict. Do you want to join the leaders of Industry 4.0? Can you afford not to? Then our advice is, plan ahead. Fight radical change with integrated radical action. And embrace the fact that it's time for manufacturers to step up and start making smart, bold moves. If you don't, you could be left behind. You have this chance. Let us help you take it.
So I'm just going to open up for a little bit of discussion now. Are you seeing some of these technologies coming into your factories at your, the shipyards or the air side of things? Are you starting to see a lot of the integration they talked about with suppliers, the cloud-based systems?
I think we're trying to. We've got too much things going on. It's difficult to implement.
Yeah, it's there is so much opportunity out there in terms of what we can do. And I noticed Volvo cars. They've I was reading an article on them. They have made a promise that by 2030 they will no longer be making petrol or diesel engine cars, and they will no longer. If you want to buy a car, you'll have to buy it online, and they're talking about kind of more customization, so you can go online, a bit like when you're ordering if you want to customize the trainers that you order for going out running, or your football boots or whatever. You can start to do that with cars now online. and Volvo sort of leading the way in that. So there are opportunities, and you've got to kind of make a start. Another company that I was doing a bit of research with, they're in logistics, and they were talking about how they've got really sort of narrow time slots, and everyone's got to buy into it. So in terms of quality, the governance is now becoming really really important. So in some ways, while it offers a lot more flexibility and choice, it actually restricts you in terms of, in other ways, in terms of the governance has to be really tightly controlled, because if one part of it fails, the whole system falls down. So I think people are still trying to get to grips with that, and we're, looking to emerge and develop, and that's why that this of Industry 4.0, Quality 4.0, we're still the way it's still being researched, but it will bring about, as that video demonstrated, some radical change. So let me go back to sharing content.
I mean, from the sector perspective, we are kind of seeing, them sort of technologies kind of come in, but the kind of having them, the kind of setting up individual cells and seeing what the art of the possible is, with like pick and place type robots, and almost having a cell whereby they're calling it cobotics, so where people and machines will interface with each other, and technologies like that for the future kind of assembly and manufacture of aircrafts going forward. So yeah, in the air sector, we are starting to see them sort of technologies kind of being developed and seeing, what's possible going forward.
Definitely, and that really does have an impact on not just how you're producing and how you're working, but also on the quality side as well. How you are governing that, and also in terms of how that is helping to improve quality and predict quality as well. Do you do 3D printing? Have you got 3D printers for any parts? You might in the air side again, more so than the shipbuilding.
Yeah, we've got some. Yes, we've got some 3D. Sorry, I'm getting a bit of feedback, so I don't know if my internet's quite good. Sorry, I'm sorry about that. If anybody else is hearing that, so we've got some 3D printers. There is a desire for us to print more and more stuff, but yeah, we've got round about 2 to 4 components now actually approved for flight on aircraft, on Typhoon aircraft. So we are starting to move into printing. So they're kind of like plastic type stuff for air ducting and stuff like that. And we are looking at actually printing metallic type components, but at the moment the accuracy isn't quite there for us to print like a structural kind of part. We're possibly looking at them from a trying to print a forging that we can then machine later to try and cut our delivery time of getting raw material or forgings in from the supply chain, which are the longest lead item on some of our aircraft components. So yeah, we're looking at them sort of technologies as well.
Yeah, that sounds fantastic, and that will bring about improvements for the business, as you say, in terms of the lead times and I guess the measurement of it as well, because the 3D printing can be fairly accurate too. So let me go back to the PowerPoint. Here. You can see my PowerPoint now, is that correct? Can you see the PowerPoint?
Yep. Yeah.
Yes.
Yeah.
So if I move on to the next one. So that was just a little bit of history and where we are today. And as I said, we're on this new industrial revolution, and you can start to see, obviously in the air side, you're starting to see a lot of those technologies coming in and how useful they're going to be for you. So in terms of what is quality, I don't know if you can see the full screen I'm seeing other things here. Let's close that there. David Garvin,
Michelle,
management. Yeah.
I just want to ask you that. Obviously, I've worked in the aerospace business and now I'm in the shipbuilding business, and you said that you kind of started out in the shipbuilding side of things. Would I be correct in saying that?
That could. I did my apprenticeship in Ailsa Troon and then Ferguson and Port Glasgow.
Yeah, it's just because obviously for it come in and said obviously for the implementation side of things for us, it can be a bit difficult. Did you find, see all these tools and techniques that you've got at the moment? Did you find it hard to implement that in the shipbuilding business?
When I was in shipbuilding, didn't really look at quality improvement at all. It was more to do with commissioning of the ship. And then we did have, it was BS 5750 at the time, I'm showing my age here, which was the predecessor to the ISO 9001 series. So we were looking more at the quality assurance, we did do sort of validations of design as well, and it was commissioning in the end of the day where we were inspection. So we didn't at that point have a quality improvement, but what we did have is we did have daily meetings where we looked at some of the problems and we used engineering to improve a lot. So it wasn't at that time a kind of quality improvement drive. As such, wasn't labelled as quality improvement. Just it was more solving and correcting quality problems than trying to address them at the root cause and prevent from happening in those days. But in terms of my knowledge of shipbuilding, and I came through the design side planning and production. I did my apprenticeship as well, so I'm quite familiar with how it is built and in the modular level. And there's lots of scope in there for doing your root cause analysis stuff. There's scope in there for looking at what we're going to cover today is a little bit on tolerances and what process capabilities we can build in as well. What's more difficult is when you don't have a large amount of products, so you don't have large batch sizes, you know, you're doing things one-off, your quality tends to be, so so you're not getting that kind of, in every part, you're not getting that repetitive data that can help you do your SPC as such, but you can apply it to the single ones. So for example, your weld, you say, you know, you'll have your, I don't know if you've got automatic welders or whether it's semi-automatic welders, don't know how you do that, but there's certainly areas there that you've got both. So there'll be areas there where you can, you know, apply it to. You'll have your cutting processes as well, where you're cutting your plates. You know, you'll have done your nesting, you'll done your plates. So there'll be bits in there that you can apply it to. In terms of your modular manufacturing, I take it you still build in modules and then assemble them in the ship, is that correct?
Yeah. All that's probably still the same as from when you were here. Or in the ship.
No. Yeah. So, you know, in terms of bringing them together, when you're looking at the tolerances and the specification, it's probably more critical on the air side of things. But in the shipbuilding side of things, when you're starting to bring modules together, you've got to have confidence that they come together. You're not going to have, you know, I guess, pumps that are piped back to front, or you've got modules that don't fit together and you've got a gap. You know, you've got to have that quality control in there. You've got to have your quality checks. There'll be areas where you think you can improve. Where are your lead times? What's most difficult? Where's your waste? So next week, I mean, I know you'll have a big lean manufacturing drive. You'll have had it at some point. So when we talk about lean manufacturing, that will certainly be relevant to you as well. But in terms of the quality, you've got to ensure your product And to do that, you've got to look to improve your processes. So you can use the tools and techniques, but it might not be that you have a control chart on on everything that you do, but you might have to look to put them on things, as I say, like the welding machines. You could put it there. Does that help?
Yeah, no, definitely. We can't use those techniques, but it obviously starts for me at the design stage, and then obviously onto a model, and then through it branches through every other department. So for the stuff you're saying, for the quality stuff, for a manufacturing engineering point of view, we're constantly looking to improve those processes. So no, we definitely use those tools and techniques.
Great. In terms of what is quality, if I come back here, we have to really understand that it means different things to different people. Now that's fine if you're making a car, because you can then identify what your customers want, and you can customize it. In terms of you're not making yachts, you're not making luxury yachts or sailing boats, you're making big vessels. So your customer viewpoint will be probably quite well defined. The customer will have its specification, but that doesn't mean to say that these first 3 bullet points don't actually apply to your customers. Your customers will want something that meets their needs and want it to do what they want it to do. And want to be delighted as well. Every customer, if you delight the customer, they're likely to come back, and that's quite important. And then the customer's specification of quality. There's also the customer's expectation of quality, and then after that, there's the customer's perception of quality. So when you deliver to your customer, you deliver based on what their specification was, what their expectations are. You've got to meet that, and then if you have met it, have you met their perception? And there are potential gaps in here from what the customer viewpoint is and what the manufacturing viewpoint is. And there could be a gap between the customer's expectation and the customer's perception of the final good. And that again is a gap and is a problem for you as the manufacturer. Sometimes the viewpoint is affected by previous experience. So if they're a repeat customer, word of mouth communications. So all of that affects quality. Manufacturing viewpoint is the management's conception or concept of the product, what it should look like, and the organisation's specification of quality. And again, what the customer specification is and what the organisation's specification of quality is. I can show you this diagram if you've ever seen this before. In terms of what is quality, you can really see the gaps in this first one. So this is a tree swing that the customer wanted. As sales specified it, it's already changed. Marketing and planning requested it. Marketing planning requested it as a three-tier one. Engineer designed it, actually made it, and of course it had to be installed differently. Now, when I go back to my shipbuilding days, I decided to be a mechanical engineer. I wasn't on the naval architect side. But in the engine room, I had to design seats for pumps. And, I would design my seat, and then I would go onto ship into the engine room to see, when it was installed, what it was like. And I have to say, it looked absolutely nothing like I designed it. Now, the customer didn't have a say in, specifying the seat for the pump or whatever part in the engine room. But it was interesting that, as it was designed, it was different here. And that, there was a disconnect there. So what was the problem? Was the problem it wasn't designed correctly? or was it the problem, or was it not a problem at all? Did it even, you know, need a design when the fitters would put it in as they wanted? Don't know if that still happens. I think probably technology's moved on now that it doesn't happen quite like that. But it's something to be aware of. And what we're aiming for, quality, is what the customer wanted is what is actually sent and serviced and installed in the end of the day. So that there isn't this gap between the perception, the expectations, and what, you know, from the customer point of view, and there's not the difference between the customer specification and the product specification. Now, the other thing I remember from shipbuilding is sometimes in shipbuilding the customer specifications were not achievable, and both in terms of the cost, but also, you know, unrealistic expectations. And part of that, you know, my job in design was really to work with the team. We had to look at how do we manage those expectations, and the negotiations in terms of the specifications actually took quite a bit of time, so that we had agreement on what the final specification would be. And I guess that's probably still much the same if you're going to a new product. I think if you're doing repeat products, it might not be that issue. But if each ship, each ship is unique, but if there's a change in the type of vessel you're building, then definitely there'll be that kind of discussions between the customer and the designers on the specification that's agreed in the end. So why do we need to focus on quality? So that's kind of like, what is quality? The most profitable companies focus on quality. And one thing that we need to capture in what we do, and again, that comes through the design phase, and going back to that little tree swing, or, you know, the most profitable companies capture the voice of the customer, so the customer gets what they wanted. But also we want to avoid quality disasters. So we want to avoid things like Grenfell Tower, from a few years ago, the Volkswagen, the emissions crisis. You could even say that the financial crisis that we went through was a quality problem. And again, it was through lack of regulation, a bit like the Grenfell Tower. You could blame that on regulations, which, you know, quality related. The NHS, and I'm not knocking the NHS at the moment, I think they're doing a marvellous job, but they have something called never events, and the never events they are things that shouldn't happen. So, for example, you would have somebody operating on and they get an organ, the wrong organ taken out, or the wrong limb removed, or parts left inside inside you after an operation. So these are called never events, and unfortunately, you know, within the NHS, these do happen, and these are catastrophic. They can lead to loss of life. If you've got the wrong limb removed, you know, even if you don't lose your life, it's still a disaster. And the NHS actually keep aside quite a huge budget in terms of litigation, in terms of negligence claims. So how do we control that? And we have to do that through our quality system. So we need quality to ensure these disasters don't happen. BAE Systems, the aircraft industry as well, again, you've got to be really careful that you avoid your quality disasters, these events that should never happen. I don't know if you're familiar with the Apollo 13 story. The Apollo 13 flight, it was the one that was going to land on the moon after the previous landing. I think it started in 1967. And what actually happened was it took off, and during the flight there was an explosion, and then they had to get the crew back to Earth, and there's a lot of really good engineering stuff going on in there. But the reason the problem happened in the first place was a quality problem. There was a problem with one of the oxygen tanks, and testing had picked up the problem, but they still went ahead and signed it off. So all of these things come down to poor quality in the end of the day. Examples in your own company, whether it's the air side or whether it's the shipbuilding side, you know, have you had quality disasters that haven't been picked up and perhaps should have been picked up? You know, where there's a poor quality. Now, it might not be a disaster, but it could be penalties in terms of, you know, customer warranty, etc. So it would cost you. So it would come down to quality costs. Anything that you can share, I don't know if it's confidential and you can share it, but you know, even if you don't, you can think of things.
There was a good example.
Yeah.
A good example, shall we? I think we were building some Typhoon aircraft, and 10 get released into the customer without some holes being debugged on the rear fuselage. That's a big impact on the customer because they lost about a third of their fatigue life and usable life for that aircraft for 10 of them are in the fleet now. That was missed. That was missed due to some quality checks being missed.
Some quality checks were missed. Yeah, I mean, something similar happened in one of the shipyards I worked in. It will remain nameless at the moment, but there was a design error where they put in the design calculations and the density of aluminium was put in instead of steel, and it was never picked up. And even though there were warnings all the way through the manufacture of it, the overall problem didn't really surface until it was launched into the water, and it sat with the water line, and it failed the stability tests. So that should have been picked up earlier. It should have been picked up at the design check. When we had to order more steel, obviously we could see that there was a problem. Why are we having to order more steel? So that was a really big problem for us, a quality problem. So quality failed there. The one you talked about there, was that part of the, was that a cost to the company then? Was that a quality cost that you incurred?
I was the customer side at the time, so the cost was probably incurred by the customer on the operating end, because left us with a kind of gaps in our capability.
Okay, but there was a cost somewhere along the line, and also a dissatisfied customer, I guess, too. So you could probably find small examples and big examples, and the whole idea is getting a robust quality system that we can build quality into what we're doing. So I'm going to show you another video now. I'm going to stop sharing here. And let me just try this one. Okay. Right, I'm going to go through this rigmarole again and see if I can share the web browser. Apologies for my dog barking. We've ended up with a delivery at the wrong time. Of course, now I can't actually get it because, let me see if I can pull it down. Right. Can you let me know if you can see and hear this one, please?
Can see it, can't hear it.
Right, hi now. I'm trying to think how I did it the last time. It's not going to let me do that. Bear with me till I can't remember how I did it the last time. It wasn't that, it was definitely share web browser. If I go to share content. Okay, I'll just try again. Can you hear it this time?
Yeah, it's starting to work now.
Okay. I'm going to mute myself as well while my dogs are barking, but hopefully you'll be able to hear it just the same. Oh. What's happening here?
One of the most important ways to growth and development is to embrace, integrate, and strengthen quality in all phases of our.
Okay. Now, just to check that you can see and hear this, can you?
Yep.
Brilliant.
Very carefully the situation of a major malfunction.
Nancy and I are pained to the core of the tragedy of the shuttle challenge. This is truly a national loss.
I am deeply sorry for any accident that Toyota drivers have experienced.
They potentially had the best answers, so I know whose ass to kick.
Quality is like our health. We tend to take it for granted and only notice it when it fails. As we have seen, it only takes one small error to have a massive disaster. Let me thank you for embracing quality and for doing everything in your power to ensure that here at ESCOM, quality comes first and that it becomes a way of life. And
Quite thought-provoking, that video, isn't it? When you can see the real problems that could have easily been avoided. But it's great in hindsight to look at that. Any questions up to now? Any comments anyone would like to make before we move on? Nothing?
No, happy with that.
Okay. Let me share my PowerPoint again. I don't know. I'm not doing too well in these sharing. Let me just close that down. Try one more time. PowerPoint. That's better. So we should be back to my slides now. In terms of defining quality. We've got 2 or 3 definitions here. Joseph Joanne talked about it being fitness for purpose. Fagenbaum and a similar one from the American Society for Quality talk about the total product and service and maintenance through which product or service meets the expectations of the customer. So it's going back to some previous slides in that meeting those expectations and making sure there's no gaps between the perception and the customer expectation. So it's capturing that voice of the customer throughout everything that we do, ultimately, according to Phil Crosby, who was quoted on that video. So how do we then meet that conformance to specification? So how do we make that fitness for purpose, if you like? Well, the first thing is we've got to define, well, what are the quality characteristics that are important to the customer? So what's sort of critical to quality? And then step 2, and I'm going to take you through the rest of the morning. I'm actually going to take you through each of these steps and try and build in some of the quality programs and issues for yourselves in manufacturing. So the first thing is, what are the quality characteristics? Second, how do we measure those quality characteristics? The first one is kind of variables, and that's your dimensions, if you like, your weight, it could even be temperature, length, diameter. So these are all things that you can put a numerical value to. And you've got this more attribute type. So you're talking about pass or fail, go or no go. And you might, certainly in the shipyard, we used to have go, no go gauges for parts where we were checking. But you would look to, well, what do we measure in terms of the variables, and I'll come back to that after as well. Part 3 is, well, okay, once we know what we're going to measure, what's the standard we're looking to achieve, and we're going to look at sort of what are the standards that can be acceptable for the customer, but also acceptable for the company. Because you've got sort of cost associated with, reaching standards and maintaining standards as well. So, where do we set that quality standard for each characteristic? And it's not just about cost, it's also about customer expectations, but it's also about technology available. If you set the standard too high, do you have the equipment that can actually measure to ensure the accuracy of the tolerance that you've set, for example? Set your standards. The next stage is really about controlling the quality against those standards. But where do you actually apply those checks, and how do you go about measuring to ensure that you're meeting standards? So do you check incoming materials and incoming goods? I suspect you do. The whole ethos of quality, though, in the supply chain is that you shouldn't have to, but I think most companies do have some kind of inspection. What you need to worry about is if you're having to, because you're not confident in your supplier, that you're having to do 100% inspection when they come in. So how should where in the process, so if you've got maybe critical processes, or critical parts, you need to put in inspection or testing points or measurement points. If you've got a high defect rate in a particular process, you might want to put more quality checks in there. Or your assignment that you've been given, the assignment brief, you're asked to identify sort of quality indicators. So things that you should be thinking about are, what are the characteristics? What are the measures and standards associated with them, and where do we measure those within the process? And are they needed, or do we need others? So this is the sort of thing that you can think about. part 4, you know, as part of the controlling of those standards is, you know, how they're conforming, and how we're going to sample. Are we going to sample 100%, or you know, is it not going to be a sample? In other words, are we going to take a proportion so that we can predict? And there's all sorts of things in there, like, you know, if your test is known is destructive, then it's unrealistic to sample 100% because you're going to destroy each part. And so we're going to look at different types of inspection methods today as well in a bit. But it's, again, you know, what if we're sampling, how confident we are in terms of what the samples are. So, for example, if I take, you know, students' work, I might have about 300 students and they've submitted an assignment. If I sample, say, 20 of them, but I only take the top 20%, you know, that have the top 20 students, then I might not get a representative picture of what's happening. So I might not be able to maybe improve and whatever, if there's a problem there, if there's more failing, that sample is not representative. So again, you've got to look at, you know, if you're sampling, how are you sampling, and what sort of errors have you got to be aware of there. And then finally, 5 and 6, in terms of conforming, you're looking for root causes of poor quality, and this is where your continuous improvement comes in, and where some of the tools and techniques of quality that you can apply there. So some of your root cause analysis, for example. So in terms of defining the sort of aspects of quality in a product, some of the things that you can look at. Now, this doesn't necessarily have to be the final ship or the final aircraft. It could be part of the module, it could be a component within it. So it could be something that you produce for another part of the assembly. So what is functionality? So how well does it do its job? It might be appearance, so are aesthetics important? Other things, you know, you would need to consider, and again, when you're looking at your quality indicators, what are the characteristics in terms of this product? Is it reliability? So what's the performance over time? What's the time to failure? Another aspect would be the sort of durability. Can it provide a useful life? And certainly in ships and aircraft, you would hope so, but in components within that, you know, how often do they need repaired? So what's the durability in terms of the maintenance for the customer? If it does fail in service, how easy can you solve that problem? So ease of repair, if you think, so that's a kind of recovery characteristic. But you've also got the service characteristics as well, in terms of, you know, the contact, person to person, knowledge of staff if there's a technical issue. So, you know, these are all different aspects of quality that can be measured. The second, so that's to do with sort of I guess the product features, but also in terms of quality, it's freedom from defects and absence of defects or out of tolerance conditions. So what we want to do then is make sure that the design is fit for purpose as well as the manufacturing. So I'm going to put you into breakout rooms now, and hopefully you will all be in something that you're familiar with in terms of a product, or which, as I said, could be an assembly or a sub-assembly part, but something that's manufactured in-house. And I want you to determine what the quality characteristics are and how they are measured and how the standards are set. So I'm going to get you to do this exercise in a breakout room. We'll come back and then we'll have about a 10-minute break before moving on to the second half. So really just to steps 1 to 3. Any questions? Is everyone sort of okay about this exercise? You're clear on what you've got to do?
Yep.
Yeah, okay. So I'm going to stop sharing. If you can, maybe take a screenshot of this exercise, or if you refer to the PDF file that's up on your platform, your VLE, that exercise is in there. So it's basically pick a product or a part that you manufacture, and then what are the quality characteristics, and again base that on the functionality, appearance, reliability, etc., and how are they measured, and what standards are set, and then we'll feed back. So I'm going to stop sharing, and I'm going to put you in breakout sessions. I think there are 18 of you, so I'll put you into 3 groups of 6 to do this. Why is this not working? And I'm going to assign you automatically, so you should just be put into groups automatically. So any second now, you'll leave this room. I'll give you about 15 minutes in which to do this. So we'll come back in just before 11 and before we have a break. I don't know if I can put timing in. Here we go.
Hello.
Hi.
Hi.
Okay, how did that go? How did you get on in your breakout rooms? All right?
Yeah, fine. Yeah.
Good, good.
Great. What I would quite like is, what I would like is for each group, for someone in each group to sort of feedback on, you know, what product line or part you took and what were the characteristics you identified and the standards that you identified within that. So start off with group 1. I think that was Louise's group. Is there someone there that would like to feedback?
Yeah, we looked at seat manufacture and installation, so the kind of quality parts that we had to that. So we spoke about the steel grade of it to make sure that the material that we're buying in is fit for purpose. It's the right strength for the equipment that it's going to go on, and obviously it's the right specification for the category of seat that we're doing. So we've got Cat A, B, and C seats.
Yeah.
Please correct me if I'm wrong, anyone. And then we looked at the fabrication side of it, so the quality standards that we have, so the user checks for the welding as well, the kind of welding standards that we use for seats, which is predetermined by the welding department for the weld procedures. We also spoke about the checks for the dimensional checks of that as well, and quality get involved in that at that stage as well. And then obviously when you take it to the ship to install, you either offer the equipment up to it, or you take the drawings off of, you take the size off of the drawings. If you're taking the size off the drawings, then quality and dimensional control need to come and check with their pre-calibrated measuring equipment. I'm a bit ignorant to which equipment that is, because that's not my job. But yeah, we basically spoke about them checking those holes, making sure that that's fine pre-drilling, and then obviously you get your welding the seats to the deck, the same kind of weld procedure, and then the kind of painting standards that would be done once those holes have been welded, once those holes have been drilled and the welds have been done as well.
Okay, excellent. That's really good. We can talk more about some of the equipment and the measures afterwards. But what are you looking for in terms of your quality checks on the weld? Are you looking for porosity, or are you what's the
weld bead thickness? Make sure that you've got a consistent weld. Make sure that your stops and starts have been ground out. Make sure that there's no inclusion of anything, depending on what kind of welding it is. Just making sure that it's a good standard, and make sure you've not left any gaps.
Yeah, okay, that's great. And I don't know whether they use X-ray equipment or whether it's an observation check. But again, these are... What's that? Sorry, Louise?
We do quite a lot of non-destructive as well, so I would imagine that would have a big part to play in that.
Yeah,
but I'm not sure.
Yeah. Okay. No, I think probably NDT's techniques would be utilised there. That sounds good. So who was in group 2? Next group, if someone could feed back there.
I think that was maybe us.
Okay.
So we were dealing with the bending of pipes within the pipe shop. So we've recently worked on a procedure for the checking of that, as there was currently no procedures within the pipe shop for quality. So we were involved in that the last few weeks. They're creating a quality standard from the defined mil spec standard that's issued to us. So basically, what we're doing is once the pipe is bent, it then goes through like a kind of 3-check quality procedure where we check for minimum wall thickness using UT and ovality as well. So what we do there is once the pipe is bent, we've also got the third step, we've got a visual inspection board where we now can compare the pipe bend to defective parts and conforming parts. So with the visual standard will show you kind of lumps, bumps and scratches that shouldn't be on the parts. And these can be checked by using a drop clock to get into the scratches, and if they're above 5 thou, it's deemed as a failure. And we get the quality inspection team to check the minimum wall thickness using a UT gauge. So they come out and they can check with that. They can also check the minimum wall thickness with a ball mic just on the regular non-bent area of the pipe, and then they can use that as the comparison. And then in terms of the, like I said, the visual standard that says you can just look at that from the board.
Yeah, that sounds good. And so personally, that you use, I take it because your customers will be Ministry of Defence, you use their military standards for that?
Yeah, that's correct, yeah. So we looked through the mil spec to see what was applicable. Ovality as well, that is also checked. I think 2 millimeters across. We use vernier calipers to check for that across the full diameter of the pipe, across the bent area and the non-bent area.
Okay, that's really good. Thank you. Thank you, Gary. And again, these are things for the assignment, so you could take that process as well as part of this assignment too. And next week we'll build on that in terms of what are the wastes and the different wastes within those processes. So that takes us to group 3. Who would like to speak for group 3?
I think that was us.
Okay, thanks.
Unless I'm wrong. We looked at something similar to Gary, which was pipes produced in a pipe shop. It's got some bit more spool pieces as opposed to bending for the pipes. So we defined the quality characteristics as the dimensions end to end of the pipe, and also the bores as well. The material specification, sure it's made from the correct material. The finish, including the paint spec, supplied by the customer, cleanliness of the pipe, the capping, ensure that it was capped prior to dispatch to the customer, weld quality, flange standard and the pressure standard that the pipe was produced to. And in terms of meeting those, measuring those characteristics, then also being produced in accordance with the manufacturing instruction that's been made by manufacturing engineering, following welding procedures which are normally included within the MI, complying with the customer paint spec, NDT on the welding, producing a verification record for the pipe, and visual inspections carried out at ship prior to installation.
Okay, that sounds good. So I think you've got everything covered there, and interesting. And I think the second group, they used sort of I guess the pass, the go no go type attribute testing, and the ultrasound thickness testing. You mentioned NDT as did the first group, so would that be the kind of ultrasound stuff in there that you?
Yeah, that's good. That'd be for the welding to the flanging, because my understanding is the pipe will be brought in as pipe stock and you cut to size.
Okay, so it sounds pretty good. I'll be going on to talk a little bit more about inspection in a minute, and then we'll be looking at tolerances within that before we move on to SPC. So I guess you're all ready for a break. We've been going at this for an hour and a half now, so if you want to have a comfort break and meet back at 11:10, would that suit everyone?
Yep.
Cheers.
Okay.
Yep.
See you at 11:10 then. Have a little break. Are we ready to go? Is everyone ready to go again?
Yep.
Yep.
I'll share my content. Right, so step 4 in conforming to the requirements is about sort of controlling the quality against the standards. Now, you've all identified what the measures are that you need to take in terms of the process that you identified earlier. How do we ensure that they're conforming? Well, I think you already identified some of the methods that you used. Critical to this part is you know, the methods that you're using, but also where and how the check should be performed. So where should we check conformance to standards? As I mentioned earlier, is that going to be incoming goods? And part of that process is about classifying the characteristics that you identify. So how critical are they? What's the cost of failure? You know, do they have is there a high defect rate? And then are they critical that we need to check after the process to ensure that there's no non-conformance? And then secondly, we've got the sort of, you know, what are the sampling decisions that we need to make? Is it going to be 100% inspection? And we don't actually know that 100% inspection, or at least manual inspection, is accurate. In fact, we can guarantee that there will be defects that get through that we miss if it's manual inspection. So some of the sampling decisions, you want to have a representative sample. And part of that representative sample is that you don't want to incur errors in the sampling. So you've got sort of type 1 and type 2 errors. And type 1 error is basically you take action when the situation didn't warrant it. So the sample that you've taken shows that perhaps a high defect rate. So you actually initiate a root cause analysis and investigation into it, when in actual fact it wasn't representative. Type 2, on the other hand, is take action when you didn't need to take action. So those are the two types of errors that you've got to actually watch out for in your sampling. And sampling plans exist. So the quality department will advise you of what kind of sampling that needs to be taken. What you've got to be conscious of is that sample representative. Are you getting correct data there? The other thing that you've got to consider is you talked about gauges and the measuring equipment, and I heard someone talking about calipers as well. So you need to know that you're not incurring, every measurement incurs an error as well, so there'll be a measurement error. So you need to be confident that the equipment that you have can actually measure to the specifications that you require, or the tight tolerances. And again, that's probably more critical for the aircraft, for the air side than the naval side, than the ship side. I know when I worked in the semiconductor industry for a while as well, after shipbuilding, and in terms of putting chips into printed circuit boards, so we manufactured the chips, the wafers and the chips, and then provided parts to the likes of IBM, Siemens, etc. And what we had to do was we had to measure to such tight tolerances for some of our customers, but we find that our equipment wasn't actually capable of measuring to such tight tolerances. So that needed reinvestment. So again, you've got to have confidence in your measurement system there. And then we can look at later on in terms of, inspection is almost after the event, although you can put in inspection points early to pick up problems earlier. But what we're wanting to do is look at statistical process control to ensure that, we're predicting when there might be a problem, and that's something we'll look at afterwards. So in terms of inspection, are we doing manual inspection? Do you use manual inspection? Well, you talked about visual inspection and go, no go, or pass, fail. So manual inspection can be expensive, especially if it's applied to every part in the batch, if it's 100% manual inspection, and it incurs human errors. And I'm going to give you a quick demonstration on this now about why inspection doesn't work. So what I'm wanting you to do is I want you to read this paragraph. I hope it's clear enough for you to read, but I want you to give me the total number of Fs. Now that might be small or large, just bulk them together and give me a definitive number. I'm going to give you a couple of minutes. I'm not going to give you that much time, just a couple of minutes to read it and then tell me how many Fs. And I want everyone, you can put it in the chat function and tell me how many Fs each of you actually come up with. So let's start now. Let's read 5 fearful fellows fought a frightful fight on Friday afternoon in Fife. 4 of the 5 fearful fellows fought for 15 minutes, but one of the fellows found a fist in his face in the first 5 minutes, which finished him off. Finally, 4 fat officers finished the fight, and the 5 fearful fellows faced the full force of the law. How many Fs in that paragraph?
I'm counting 45.
Same.
45. Any others?
I know for a fact I'll be wrong, by the way, at 45. So that's true.
I get 45 as well, actually.
Damn it, I got 46.
I got 47.
I got 44.
Yep, 46.
Does it include the yellow line?
No.
Good for thinking out the box, Louise.
Louise throwing a curveball into it.
Love a Wednesday morning curveball.
44, 45, 46 and 47. I can't tell you, I think the answer is 47. A word, an F count, I guess, on that. What this exercise is just to prove that there's variation in terms of manual inspection, and carrying out 100% manual inspection is not 100% effective, and that's something that you've got to be aware of. 44 to 47 wasn't actually bad. I've had 38, and I've even had people going over 47 and telling me, 50 and things. I don't know where they got that from, but perhaps maybe they were counting the effective down at the bottom as well. So, there can be a range, and it's not foolproof. It's not mistake-proof, 100% inspection. So let me move on here. A lot of companies then go to 100% inspection, so that's in terms of separating parts into acceptable and unacceptable quality levels. And a lot of industries use that. They maybe set up vision systems and cameras to do that. And that can often feed back to some of the upstream operations. So if they're getting parts that are coming through that are failing, they can feed back so that adjustments can be made to reduce any variability here. So that's sort of automated inspection. So some of the techniques that you can use in terms of automated inspection, you've got coordinate measuring machines that can be set up, and these are contact. But you can also have non-contact measure machines, which tend to be vision machines, so machine vision. You've also got lasers, and there are other non-contact techniques out there that can be used in more of a kind of mass production, if you like, sense, particularly if you're doing 100% inspection. On the air side, do you use some of the machine visions, lasers and things in terms of 100% inspection? Can't remember who was there for the aircraft side.
Sorry, what was the question again? Sorry, Michelle.
In terms of inspection, do you do 100% automatic inspection on some of your parts on the air side?
I wouldn't say 100% automatic inspection. No, I mean, because of safety critical items, we will kind of every structural part, which is more or less every part on the airframe, will go through a CMM. But yeah, that's not automated. But obviously the CMM program itself is automated, but the loading, unloading and setup isn't kind of automated. It's not like it's on like an assembly line, like in the automotive industry where you've got automatic checking fixtures on the line. But we do 100% inspect quite a lot of stuff, and probably too much stuff as well. We probably incorporate stuff that's highly capable features in our CMM programs, and then we're inspecting them to death because we put them in at the start of a project and then we run out of funding and can't take them out thereafter. So we end up tying ourselves in knots and inspecting everything forever throughout the life of the project. So yeah. Take on board the point that it's not ideal.
Yeah. In terms of safety critical though, you would want to put in more emphasis on inspection for safety critical parts. What perhaps you were talking about there is some of the parts aren't safety critical and possibly don't need that level of inspection. So again, there's an opportunity there for improvement in terms of
I think you're absolutely right, Michelle. The thing about it is that we'll identify a part that has a really, really good CPK, PPK, if you will, good quality indices, and we'll say, all right, you know what, let's inspect this particular product. 1 in 3, 1 in 5, but our factory systems can't they're generally too rigid for us to say, to set it up in our factory system to pull out 1 in every 5 part, and that's where sometimes it falls down.
Oh, that's
that makes
quite
sense.
interesting, because we're about to go on to CPs and CPKs in a minute.
Yeah.
So so that's quite good to note that. Steps 5 and 6, once we've got the control in place, we've got inspections, what we'll find is that there will be variation in the parts, and variation comes into sort of 2 causes. You've got random or common causes, and the first kind, and assignable or special causes in the second kind. What you've got to be careful of is the common causes are inherent in the system and generally need a sort of more management decision making to try and reduce those further. The assignable causes and special causes tend to be more easily identified. It's if something goes wrong, so perhaps if a cutting tool breaks, or if there's a change in shift and there's an operator that hasn't been trained that's working on something. So you might find that those are more easily identified. The random and common causes are more difficult to reduce, and we tend to base our process capabilities on what's happening within the normal or the natural variation within the process. So move on here. One way of looking at this is statistical process control. Move that up. Hopefully that will disappear in a minute. Right, okay, so statistical process control. So what we're trying to do here is we are trying to assess and analyse the variation in the process. So identifying the common causes and the special causes that you find in your process, and trying to reduce them. You will never completely reduce the variation, the common variations, but the assignable ones, as I said, are usually more easily identified. And the whole idea of SPC is that you identify them before they happen. You can start to see trends that are coming out that alert you to the fact there might be a problem in this process. The sort of methods, include, production data, check sheets, histograms, the process capability and analysis, which we're going to go on to in a minute, and control charts, which again we'll cover today. Using control charts on the side, I think, will be quite interesting. But if you've got standard processes, then they can easily be applied in there. And they are the most widely used SPC methods. Process capabilities let us know really just how sort of capable the process is. Now, was it Robert that was speaking there? I can't remember. Somebody from their side said that the processes that you're measuring are capable and only need a sample approach, but because of the system, you were doing 100% checking on them. But in terms of the sort of process capabilities generally, if you think of your histogram, we're basing it on a normal distribution, which means it's centered on a mean, and there's a bell-shaped curve with the mean and the median, if you like, in line, so that you've got a nice normal bell-shaped curve. And within 3 standard deviations of that, that takes us to the natural tolerance level. And what we want is that natural tolerance level to be inside the specification, if you like, for that part that we are producing. So generally the process capability is 3 standard deviations from the mean. So from that central point, if you take out 3 standard deviations on either side, that gives you a total of 6 standard deviation. And we've got confidence that the majority of the parts we are producing are within those 6 standard deviations. So what does that mean in terms of taking it down to using process capability indices? Well, there are two main indices that we tend to use. There are others. There's process and process. Been muted. Can you hear me? Are you hearing me okay? I just had something coming up to say I was muted.
Can hear it now.
Yeah, I think
Yeah.
you dropped out
So
briefly, but you're back.
Lost you for a second.
Okay. I was muted, but I don't know. It's very difficult sometimes with the, as I say, with my broadband. But okay, so what we're talking about is we're wanting to have confidence that the part we're producing is, we've got the confidence that it will be within specification. And the process capability indices tell us what the natural tolerances are and let us do a comparison with the specifications and where it sits. And a sort of analogy of it is, if you've got a garage, you've got a car that you're wanting to drive into the garage, what you want is you want to try and get that into the middle of the garage, and you want sufficient space at either side. If the car's too big for the garage space, you're going to crash. If you don't get it on the centre, you're going to crash. If the car's too small, then it could be that you don't need, you can tighten your tolerances, or you have absolutely no problems getting that car apart. So these capabilities let us know the size of the car in comparison to the size of the garage, and I think that's the sort of best analogy I can give you in terms of the process capability indices. So what they do is they take the upper tolerance limit minus the lower tolerance limit, and because, remember I said it was 3 standard deviations either side of the central point, and that becomes 6 standard deviations, so 6 times the standard deviation. So what's the upper tolerance limit? What's the lower tolerance? That should be lower tolerance LTL, and the standard deviation of the process variability is S. That doesn't guarantee good products necessarily, because we don't know, the CP doesn't give us the mean. It only takes into consider the standard deviation and the sort of standard deviation. It doesn't tell you where the mean is, how central it is. So you could still crash that car going into the garage if it's offset from the central tendency. So the one that we look at for central tendency is CPK. And the CPK gives us, we work out the minimum between the offset from the upper control limit and the lower control limit. So the CPL, which is the lower capability, is the average, so the mean minus the lower specification limit over 3 times the standard deviation, because remember, for this we're only taking one side of that bell curve. The CPU, on the other hand, is the upper minus the mean over 3 times the standard deviation. To work out, based on a specification range of 214 and 198. So you've got an upper limit of 214. Now this could be grams, it could be centimeters, it could be whatever, but it's a variable. There's a measure associated with it. So I've not put the units down, but it could be anything. There's a standard deviation, a known standard deviation for this process too. So I want you to calculate the CP value and the CPK value and tell me what's happening in this process. Okay, so if you take a note of 214 and 198, we know that there's a change of process average to 210. We want to know what the CPK value is. So if we go back to the previous slides, CP is the upper tolerance limit minus the lower tolerance limit over 6 times the standard deviation. That's the first one to work out. You all do that for me? And let me know what value you get there. So it's the up minus the lower over 6 times the standard deviation.
Is it 5.3? I don't know if I'm doing that right.
No,
I'm
it's not 5.3.
to be fair.
It's not 5.3.
I'll leave that one then.
Is it 1.33? No.
1.333 is the correct answer.
That's close enough.
So let's go.
That's what I want, Karen.
You got the point 3 right. Okay, the good news is you've got software to do this for you these days. The next one is the second one, which is actually an indication of the actual capability going on in the process. As I said, so this considers the average. So we know the mean is 210. We know the lower, the upper specification limit is 214 and the lower one is 198. We know the sigma levels too. So what does that come out to be? How do we work that one out? And it's the minimum of the, so we get 2 values there and it's the minimum we take for CPK. And
Would it be 0.67? That's a CPU one.
Yeah, 0.666, that's exactly right. What I will say to you is the CPK, we take the lower side, we take the low one there, and it's never over the CP value. So you can always bear that in mind there. So there's my solution there. We've got the 1.33 and the 0.66. So what does that actually tell us? You know, what does that actually mean in terms of us being able to park the car in the garage? So I don't know if you can see, I've taken this diagram because I thought it explained it very well from the Slack Brandon Jones and Johnson book. And what it tells you is if you've got a specification range, okay, you've also got your natural process, variation of the process. If you've got a CP higher than 1, then you know that you fit within the tolerance level. That's your bell-shaped curve, and that's your central tendency in the middle. So we've got confidence then that that process can produce the part within the specification range. If we have it as equal to 1, then the natural variation of the process is the same as the specification range. If it's less than 1, then the natural variation is outside the specification range here, which means we're going to produce more defect parts. We're not going to meet the specification limits. We've got poor quality and we don't have a process in control. CPK, on the other hand, looks at the shift in the mean in terms of where, or the shift from the central tendency where it should be. And we can see that if the CPK is less than 1, you've got a chance of crashing your car there. So what you're looking for is a CPK equal or equal to the process capability to ensure you've got your central tendency because what we'll find is that you have some, in this case, the upper tolerance limit. So in terms of the natural tolerance limit compared to the specification range, when we're taking 3 sigma and we're working to 3 standard deviations from the mean, we know that 0.27% will be outside the limit. And any increase in the tolerance range will reduce the percentage defect part. So what we want is we want always the CP to be greater than 1. We got 1.33. That is generally a really good process capability value to have in the last one. So what does that actually mean in terms of us designing? The over design and over tolerance parts, we're increasing the cost, and we're also making it more costly in terms of producing to those tolerances and to fitting within the specification. We're going to have tighter process capabilities. We're going to have to work to greater than the standard deviation 3 sigma. So what we're looking for is to try and get that balance. So if you've got a huge garage and a really small car, while you'll park it right every single time, it could be you could get 2 cars in there. Do you need all that space? Is that an extra cost for you? In terms of manufacturing your parts, if you've got really tight tolerance on drilling holes, for example, do you need such tight tolerances because you're incurring costs both in production and testing, because you'll need better equipment to actually test, to actually measure the holes if you're inspecting them. So closer tolerances generally mean better performance of the product. However, it also incurs costs in terms of manufacturing, both and also in testing as well. So when you're specifying your tolerances, you've got to also give considerations to these other aspects, such as cost and measurement, and any relief that you can have in terms of manufacturing. As manufacturing engineers out there, you will know that if the wider the tolerances, the better. However, in some cases, it can also be negative to have too wide a tolerance. An example of that, again, a company I was working with recently, they had a flexible pipe. They had a specification of 300 millimeters in length, plus or minus 50 mil, which is quite a big tolerance on that. But they were finding that they were getting parts close to the 350 mil. They were having problems fitting them into their product. So that was creating problems for them to have such wide tolerances. So while it was easier for them to manufacture, and they didn't have to sort of they didn't have to inspect them too carefully either, it was creating problems further down the line. So getting that tolerance fit right with manufacturing, and it's working together to agree on the specified tolerances and how tight they generally need to be. So I mentioned that earlier we want to capture the voice of the customer when we're going through this, but equally we need to know what the voice of the process is telling us. And our histograms and our control charts do that. They tell us what's happening in our process. So if you've got any kind of standard going on, so if you've got, maybe not mass production, but if you are doing a high batch size of maybe your pipe bends or your drilling, you've got a standard process going on there. You will be able to get data and set up control charts for that. And again, it's based on those 3 standard deviation either side of the mean. So here's an example of a control chart. So you can see there's a center there, there's a mean. I don't know if you can see my cursor here. If you did your bell-shaped curve here, your histogram, you would see it would curve along the center line with that central tendency there. and these upper and lower control limits. And then you would take your sample number up here and you would plot it across the centre line. Now, the whole purpose of your control chart is for you to look for trends in this data and see what's happening here that shouldn't be happening. And it could be that this is within these two control limits, this is your common causes of variation. You will always get variation there. What if you start to see a trend towards the upper control limit? So say the next 5 or 6 points in a row are tending towards that upper control limit. You can see before it actually goes out of specification, you can actually then say, right, there's a problem here. Let's take action in control, let's do a root cause analysis to find out what's going on here. And it could be, as I said, if it's your drilling machine, it could be that the cutting tool itself, the drill itself, is actually wearing, and therefore, there's points going out of specification. If it's a cutting, if it's a machine tool that's cutting, it could be that again there's wear on the cut, and therefore the diameter of the part that's being turned would be.
Michelle,
So
that's something that I would like to see implemented in the shipyard for obviously machine capability. Because I've worked in other companies where you use that. It's like your SPC chart essentially, and it lets you know if the machine's going out of specs. And as you say, there could be various reasons for it going out of spec, whether maintenance need to fix it or change a tool so your whole edge size is correct, or and how many samples you do. So that's something I'd like to see obviously implemented within all machines in the shipyard.
Yeah, Craig, I mean, I think certainly where you've got something, especially where you've got standard parts going through there, it is quite easy to set that up. And you've got software that does this analysis for you, so you don't even need to calculate, you could set up sensors that would work on that. And I think that's where we're leading into sort of these new technologies and sensors that can actually predict when you need to do your maintenance, where you need to change a part in your machine tool.
Yeah, like a preventative maintenance, because it's giving you the results before it's actually happening.
That's it exactly. But the other good thing about a control chart is, let's say a cutting tool breaks and suddenly you've got a part way out of spec, you've got something up here or something down here. Or it could be that there's a new operator in the machine, or it hasn't been programmed correctly, if you're getting parts down here. What it does help you is you can stop the process. So you can actually stop that machine as soon as you see, parts coming out, and you can reset it or change whatever's required there. So without this, what you might find is that machine is producing part outside specification, and you don't pick it up until inspection, where you suddenly find that you've got 20 parts, whereas you could have picked it up earlier. You could have picked it up on the first one going out of control. And these trends, it's a really useful tool to have, and it's really useful to implement. So Craig, thanks for sharing that. And yeah, you're right. The machines are the cutting machines, the machine tools are the best place to put these in, and there's software that can integrate with them. I know the coordinate measuring machine that we have in the university, we've got SPC software attached to that as well, so that when we're doing, maybe repetitive measurements, we can actually work out some SPC and do some control charts based on that too. So just a kind of reminder that, variations, you've got your random ones, the common ones, which are what we're only wanting in terms of our SPC, in terms of our statistical control. So these are the ones that we're monitoring. And then you've got the assignable or the special causes, which suddenly indicate a departure from the statistical control. The process capabilities let us know that our process is capable of meeting within the limits of the specification. So there are different types of control charts. there's control charts for what I was talking about there was the variables where you've got a dimension, your cutting machines or your drilling machines. You've got control charts for attributes, and that would be pass or fail. So you could set that up for your pipe bending process, for example. So that's very much more of a, how many defects are there? Is it, how many pass, how many fail within the sample? So a process that's out of control shows changes in the mean or changes in the variability. And certainly you've got these two for attributes. In terms of the variables, you've got an X bar and an R chart. So you can look both at the change from the mean, but you can also look at any changes in the range. So the range, so the minimum to the maximum that you can do. So here's an example here where you've got an X bar chart, it's known as, at the top, and you can see that you've got a distribution around that central tendency, that average, that X bar, the mean. And here you look at the range. So you've got your range here, and again, you've got what's the central tendency on your range chart. So it could be that your process is maybe the range stays the same, but the central tendency, the mean, moves. So in terms of attributes, so your pass, fail, your number of defects, you've got, again, a number of charts that can be used to, you can measure. So it could be defects per part, for example, an automobile. It could be a fraction of bad parts in a sample. It could be, flash in plastic molding. It could be a problem with the weld, or it could be a number of flaws in, a roll of sheet steel or a plate that, you've got incoming. The two types of charts that you use for attributes, you've got the P chart, which looks at the fraction defective in successive samples, and your C chart, which is number of defectives or non-conformities per sample. And again, you would plot that per sample. But as I mentioned earlier, what you're looking for here is you're looking for plotted values that lie outside the control limits. So your special causes, if you like, your assignable causes. And you're also looking for trends through wear or other factors that occur through time. And you're looking for changes in level of data or points consistently near upper or lower limits, so that it might be that your mean has shifted in. So the types of programs that utilise this, you've got total quality management, you've got Six Sigma. These both use statistical process control. You can take that a step further. You can take SPC a step further into design of experiments and robust design, or robust engineering, where you're actually building that into the design process, and that's taking it the SPC a stage further. We've also got standards like ISO 9000, ISO 9001, 2015 is the latest version, which I'm sure you'll be working to. You'll be working to your military standards on the ship side, and in the air side, I know you've got quite stringent quality standards that you have to work to on that side as well. So a whole lot of different quality programs in manufacturing. TQM is about customer satisfaction. It's a holistic approach. So it's about using those tools that we talked about, by using other tools as well. So you've got ones that we haven't covered are failure mode effect analysis. You've got Pareto, cause and effect tools. I'm sure these are things that you've heard of, and you'll have seen, perhaps you've even got that fishbone diagram that sits up on your boards for people to look at, where you've improved. Your quality department will be using those. But the key about TQM is that everyone's responsible. It's about people as much as it is about the sort of tools as well. So it's getting everyone to take responsibility so that quality is built into the product, and we're not just inspecting poor quality out. We're building good quality in. And it's about a never-ending chase to produce better products using the tools that are available. Sort of a big approach to quality, and we've got, you know, I'm a Six Sigma black belt. You've got yellow, green. You've even got a white belt, which is the very beginning, master, and then you've got up to the black belt and master black belts. Some companies have their own. I've heard of orange belt, which is kind of equivalent to the green belt. But what does it, you know, what does the Six Sigma use? Well, what does this actually mean? So I've been talking about 3 standard deviations from the mean. And what that means is that everything that you produce, there's a yield of 99.73% of what you produce is good, is within specification. That equates to 2,700 defects per million. We're going to look at the Six Sigma per million opportunities in a minute, which is different. When we're working to Six Sigma in standard normal tables, and this is where we have a disagreement between statisticians and the Six Sigma program. So the black belts and the statisticians never agree on this, because standard normal statistical tables tells us that Six Sigma means 99.999998% of the population, which is a defect rate of 0.002 defects per million opportunities. However, in the Six Sigma program, we change that yield. So we say that Six Sigma is actually 3.4 defects per million opportunities. Not that we will make 3.4 defects per million, but there are 3.4 defects per million. There are 3.4 opportunities per million for opportunities for defect. And that changes to a yield. So what we produce within specification is 99.99966. Now, the reason for that is when Motorola devised their Six Sigma process, they realized that the process mean over long runs tends to shift naturally, but that doesn't mean, you know, that we should try and fit within that 99.9999998%, as the statisticians did, that we should compensate for that. So they used 1.5 sigma as a magnitude, an allowable shift within the process. So in terms of the real statisticians, what we're talking about is 4.5 sigma. The black belts and the Six Sigma programs, we call it Six Sigma. And all it is that we take the Six Sigma, but we have an allowable 1.5 sigma shift. So if you look at statistical tables and you compare that to the Six Sigma tables, that's where the difference comes from. So by measuring the sigma level, we can do comparisons, and we can compute how many defects per million opportunities that we are actually working to. So how do we, I'm going to do the calculation of defects. Why are we talking about defects per million opportunities? We're not talking about just making 3.4 defects every million. What we have to look at is how many opportunities there are. So if you take a form, for example, and a form has 14 boxes that has to be complete a survey, then that's 14 opportunities for error. So it's about looking at the design to say, well, do you need all those 14 boxes? Now, similarly with the products you're manufacturing, you might have welds. You need all those 14 welds. can you manufacture in a different way? So I think your last module looked at how you would manufacture and optimize the manufacturing. And part of that would be looking to reduce the opportunities for error. So, if you've got a part, if you've got a module, the less parts contained, the less opportunities for error. So that's really what that actually means. And Six Sigma means that you're working to 3.4 opportunities per million. So the key terms that you need to know, we're going to do a little calculation here. We've got another half hour. The units, so the parts, components, assemblies, sub-assemblies, etc., documents, whatever needs to be tested or inspected. The quality characteristics, so this is what's critical to quality, but in the eyes of the customer. So this is the sort of voice of the customer you're talking about here. So it could be diameter, thickness, it could even be percentage acceptable, the sort of quality, the delivery time. So it's what you measure within that unit. So that's the kind of exercise we did earlier. And then defects are anything that doesn't meet the specification. So basically a non-conformity, and then the total number of chances per unit to have a defect. So anything that can be measured or tested for a defect opportunity. And note, there could be multiple opportunities in each unit. And then a defective unit is one that has one or more defects. So how do we calculate the defects per million opportunities? To know, and the reason we want to do this is we want to know what sigma level we are working to. So it's another way of telling us how capable we are in our manufacturing. So we would take the total opportunities as the units inspected, so how many units we've inspected, times how many opportunities there are for defects. And then you would take the defects per unit, so how many defects there are per unit, and the defects per unit opportunity would be the defects over the total opportunities, so D over U times O. Very simply, the defects per million opportunities, you just multiply that by 10 to the 6. So another quick example for you. Calculate the DPMO based on that. Someone's trying to call me in a Teams meeting. Apologies for that, if you can hear it. So that's the number. If you've got the number of units tested, it's 500. If you've got the total defects as 57, and the total opportunities for defect is 3, what's the defect per million opportunity? If we go back there. So unit 57, opportunities 3. Sorry, units 500, defects 57, and opportunities 3. What do you come out with there? Do you need a calculator for this?
Just give me the figures again, Michelle.
Yeah, so you've got 500 units, 3 opportunities for defects, and you've got 57 defects that have been picked up on sampling. So 100 units were inspected, three opportunities per unit and 57 defects. So what does that process tell you? Per million opportunities.
At 38,000.
Yeah, I get 38,000 as well.
Okay, perfect. So 38,000 is the DPMO. What does that, on the Six Sigma tables, what does that come out to? So if we look for 38,000, DPMO 38,000 is roughly, if you take it to the nearest, 3.3 Sigma level, and it tells you that you're working to a 96.4% yield. And that's 96.4% of what you produce is within the natural tolerance, 3.3 there.
Sorry, Michelle, see when you say it would be,
yeah,
it would be like 3.3 sigma, is that plus or minus 3.3 sigma?
Plus or minus 3.3 sigma.
Cool.
Yeah.
Okay.
Yeah, I know that can be quite confusing because people think when we talk about plus or minus 3 sigma, we're actually saying, well, the whole spread is a total of 6 sigma when we're looking at capabilities. But when we're talking about 6 sigma, we're actually talking about minus 6 to plus 6, which is way down here at 3.4 DPMO. So you can see that's the 99.99966% yield, and that's your 6 sigma. So this is what we're trying to aspire to. And this one that we've looked at, we know that we're operating to 3.3. So what does that actually mean? So I'm going to show you why 99% isn't good enough. So let me see if I can put this on, see what happens. Can you actually see this video? If you see and hear it, I should add. Of course, my network's so slow.
Don't know if it's opened in another window.
Let me just stop sharing and see what happens. It's still trying to find it. I've got it now. So I'm going to pause here. And I'll share again. Okay, can you see and hear this?
Yeah, we can hear that and see it.
It starts with
one thing. I don't know why. It doesn't even matter how hard you try. Keep that in mind. I designed this product to explain in due time. All I know, time is a valuable thing. Watch it fly by as the pendulum swings. Watch it count down to the end of the day. The clock takes life away. It's so unreal. Didn't look out below. Watch the time go right out the window. Trying to hold on to didn't even know I wasted it all just to watch you go. I kept everything inside and even though I tried, it all fell apart. What it meant to me will eventually be a memory of a time I tried so hard and got so far, but in the end, it doesn't even matter. I had to fall to lose it all, but in the end, it doesn't even matter. One thing, I don't know why, it doesn't even matter how hard you try. Keep that in mind. I designed this rhyme to remind myself how I tried so hard. In spite of the way you were mocking me, acting like I was part of your property, remembering all the times you fought with me, I'm surprised it got so. Things aren't the way they were before. You wouldn't even recognize me anymore. Not that you knew me back then, but it all comes back to me in the end. You kept everything inside, and even though I tried.
Okay, so that of why 99.9%, and if you look back at those statistical tables, 99.9 on its own closest is that is 3.9 sigma, so 3.9 either side of the mean plus or minus, which is why we really need to strive for 6 sigma, which is known as excellence. So just let me share the final few slides. So the 6 sigma process is the DMAIC process. I'm just going to introduce this before we move on to the lean manufacturing next week. And we can talk a little bit about Lean Six Sigma as well, bringing the two approaches together. But the Six Sigma really uses a framework called DMAIC, which is define, measure, analyze, improve, and control. And within each of these stages, you will use the SPC that we looked at today, and your quality tools coming into it. So you're defining the program and the objectives. You're setting the project charter. So Six Sigma is applied where you've got a known problem, where there's a problem that you need to do an investigation into, and this framework allows you to present that. So it could be at the define stage, you make the business case, you set the objectives, you go and you measure, what do we need to improve, what is the situation at the moment. So you get your baseline measures actually. So you want to look at the current state, the as is, what is it now, what's the baseline measures for now. And then you would analyse to look at any root cause analysis. You would look at factors that are influencing the causes of errors or of not meeting specification, for example, and then identify and implement improvements. And in the control stage, you're setting up your control charts and your SPC going forward. So it's quite a powerful framework, the DMAIC. You can apply it particularly where you've got maybe more complex problems. You want to go through this for this 5-stage process. So the first one is really just understanding, defining what is this project going to be about, what's the scope, where do we start, where do we finish, and what are the key metrics that are important here, what are the key quality characteristics, but also who are the stakeholders involved and how we involve them in the process. And then is there data available? If not, what should we measure? How should we measure it? Is the data accurate? So what's your calibration? Is the measuring equipment capable? And what graphs should we make? So these are all kind of things that you consider in the measurement stage. The analysis, you're looking at root cause analysis here. You're going back down to, what are the causes of the problem? So what are the effects that we are seeing? What are the root causes of that effect? And there are tools that you can use. You may already be familiar with 5 whys and root cause analysis, and you can even go into sort of bigger problem solving techniques such as TRIZ and others within this stage. The root cause has been verified, and again, this is something, if that very first video I showed at the Toyota problem, they did a sort of containment approach, and they solved what they thought was the root cause, only to find it wasn't. So they had 2 attempts at it, which caused them even more problems. So it's verifying those root causes so that we know where to focus our efforts. And then, do we have the right solutions? Can we verify the solutions work? And importantly, have we reduced the variation? And then we're setting up the new control limits and capabilities. So we want a stable process, and we're controlling and monitoring that. Last video today that I'm going to show you is this one. So I'm going to stop sharing again. Any questions while I'm setting this up?
Nope, none for me. All good.
Thank you. So this is the best, the Fortune magazine come up with, this is one of the best Six Sigma examples in the world. And as I say, my network's just really slow connecting, sorry for this. Right, I've got it now. So I shall start sharing again. I'm getting the hang of the sharing now. Can you hear and see this?
Yeah, that's all good.
Yep.
Yep.
It's stalled here, apologies for this. If it's not going to pick up, I might get you just to watch this on your own at the end of this lecture. I'll try one more time. Okay, I'm just going to stop sharing that. If you can, please watch that on your own, because it's a really good example of Six Sigma. I'm stopping sharing. My last slide just says next week we've got lean manufacturing, which I'm going to go on to, which leads on from Six Sigma, and I'll also look at Lean Six Sigma next time as well. Please do watch that Mumbai video, because it really let me see if I can actually give you the link in the chat to save onto your file. Let me see if I can do this. Where is the chat? I've got mute.
It's just bottom right, Michelle, if you have a look, it's just there.
Oh, I've got it. Yeah, I've got it there. Thanks, Janet. So that's the link there. So that really brings us to the end today. Do we have any questions? Anyone get any questions for me? Anything they want me to go over? Not sure about? Any points of interest?
No, I'm happy with how it's went today. Thank you very much.
I'm happy.
That's great.
Michelle, just a question in terms of capability. Where
Yes.
would a large international size company like BAE Systems expect to be in terms of Sigma for their output?
Now, if I remember right, from I used to be in charge of the MSc in quality management at the university quality department there. I think you were working towards 6 Sigma at one point, but I believe you achieved 5 Sigma on some of your processes. Now, that was a while ago. I couldn't tell you what it is now, but you would be expecting to work at higher levels than 3 Sigma. I would be expecting you to be towards, particularly on the air side. On the air side, you'd need to be working towards 6 Sigma. On the naval side, you know, maybe with it might not be so critical there, but certainly I would think in terms of maturity and reputation, you'd be wanting to work above 4 Sigma.
Thank you.
But as a Lean Six Sigma black belt, I would say 6 Sigma is where you're wanting to be. Okay. Well, that's if that's everything, then that's us for today. And I next Wednesday morning when we're going on to the sort of the more continuous improvement side in terms of lean and reducing waste. But for your assignment, have a think about processes and quality indicators within that, your quality characteristics and how you're measuring things in there. And after today, it might make you rethink the process that you were going to assignments and groups. Getting to know you, and thanks for all your, you know, for the discussion points and your interaction, for those of you that contributed as well. And I'll see you next week.
Thanks, Michelle.
Okay, thanks, Michelle.
Bye for now.
Thank you.
Thank you.
Thank you. Cheers.